Hello and welcome to today's lecture. So, in the last two lectures we had briefly discussed about random variables and we had introduced upon the concept of expectation. Okay. So, I will begin by briefly recapping whatever we had discussed with respect to random variables. So, a random variable okay, can be discrete or continuous. Okay. For random variable, you can determine something or define something called a cumulative distribution function. Okay. It's typically written as f of x. Okay. So, f of x is probability of x less or equal to a value x. Okay. And so, using this we can calculate probability in a regime. Let us say for example, this is nothing but f of b minus f of a. Okay. For a discrete random variable RV, so I will put RV in short. Okay. You can define a probability mass function okay, which is nothing but P of A is given by probability of x equal to A. Okay. But for a continuous random variable, probability of x equal to A is always 0. Why is this? Because for a continuous random variable, you have a concept of a probability density function okay, written as f of x. Okay. So, your probability of x in an interval b is defined as integral of f x dx over that interval. Okay. So, this would mean that probability of a is integral of a to b f x dx. So, probability of x equal to a would amount to a f x dx, and this is nothing but 0, okay, because you have the same interval. Okay. So, let us take a pretty simple example. So, let us define f x as c to the power minus x okay, between 0 to okay, and equal to 0 otherwise. Okay. How do we calculate f of x, or how do we calculate the constant? So, we use the identity that between minus infinity and plus infinity, this integral was return me a value of 1. Okay. So, I can use this expression. So, this amounts to z c is equal to 1. Okay. I can take it out. So, this comes to be so this I can simplify as c 0 is 1 minus 2 okay, equal to 1. So, implying c is equal to okay. So, you have constant as e square by e square plus 1. Okay. We then introduce the concept of expectation. Okay. And your expectation is nothing but simply the mean of the population or mean of the sample. Okay. So, how can we make use of the concept of expectation? Let us discuss few simple examples. Okay. So, imagine you are waiting in your room for a letter to arrive, okay, and the waiting time. So, x is the waiting time. So, you want to wait. So, you are expecting the letter to arrive at 5 p.m. Okay, but you have to wait, and the waiting time is a random variable x, which is continuous. and which is defined as follows. Okay. It follows the probability distribution f of x given by So, the waiting time x is a continuous distribution, continuous random variable, which follows with the probability distribution as follows. Okay. So, you ideally expect the the envelope or whatever you are waiting for to arrive at 5 p.m. Now, how long will you, on an average, how much do you have to wait? That is the question. Okay. So, how do you do this? This is nothing but, so when you say what is an average expected wait time, it is nothing but the expectation x. And this I can write as 0 to 2 half into x into dx. Okay. So, half is your px, this is your fx. So, x fx dx is nothing but the expectation. So, either way for x cannot be less than 0. So, you can integrate from 0 to 2 and 2 to infinity. Here your f of x is nothing but 0, okay, x dx, this fx is 0. So, essentially this thing is 0. So, you have to integrate from 0 to 2 half dx, okay, equal to half into x square by 2, 0 to 2, okay, 2 square. So, this will return your value of 1, which means that if this was the your distribution for waiting time, on an average you will have to wait for 1 hour to receive your mail. Okay. So, let us now do some basic algebra with expectations. Okay. So, imagine you have this random variable x and you have another variable y, which is defined as a of x. Okay. What is going to be the value of E y? Okay. So, this assumes that the probability for a given x, the underlying probability density function is the same. Okay. So, I can write E of y, if this was a continuous variable, let us say E of y is simply integral a into, so a x into p of x f of x dx. Okay. So, this I can take the a out. So, let us say I can write minus infinity to infinity, okay, x f x dx. Okay. Now, what is this? This is nothing but expectation of x. Okay. So, I will have E of y is a E of x. Okay. So, this is similar. So, you remember from long back we had done this basic transformation. If you define y is equal to a of x, what is y bar is equal to a x bar, and this is nothing but the exact same equation, because expectation of y is simply y bar. Okay. So, this is the same equation. So, we can use the similarity concept and then ask what is E of a constant c? E of a constant c is nothing but the c. So, if your variable is always constant, then on an average you always expect the constant value. Okay. So, we can generalize this and say a of x plus b is equal to a E of x plus b. Okay. We can extend this. So, let us do a simple example. Let us say that x is a variable, okay, which has discrete random variable. So, let us say discrete RV, okay, which takes on values of 0, 1 and 2 with probabilities 0.2, half and 0.3. Okay. So, I can calculate the value of expectation of x, this as simple equal to 0 into 0.2 plus 1 into half plus 2 into 0.3. Okay. On an average I have 0.6 plus 0.5 is 1.1. Okay. So, if I define a value y, let us say 2 f x, y is equal to 2 f x, then E of y is simply going to be 2.2. If I define y is 2x plus 1, then E of y is going to be 3.2, okay, so on and so forth. Okay. So, now let us say you have different random variables x1, x2, so on and so forth, and these are independent. Okay. And I can think of a random variable called x is equal to x1 plus x2 plus dot 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 plus xn. Okay. So, what will be my expectation of x, okay, expectation of x will come out to be summation E of x I. Okay. So, let us take a very simple example. So, imagine the office clerk has to put n letters in n envelopes, in exact envelopes. Okay. So, by mistake, okay, so when we say in n letters in n exact envelopes, so every letter should ideally be in one particular envelope. Okay. So, the office clerk makes a mistake and randomly mixes it. Mixes the letters and puts them in random envelopes. Okay. So, how many envelopes will contain the right letter? This is the question. Okay. So, how do we do it? So, you have n letters and in n exact envelopes, okay, to be put. Let us say we define xi is a random variable, okay, which can take in two values 1 and 0. 1 if correct letter is there, okay, and 0 otherwise. Okay. So, if you have n letters and n envelopes, what is the chance that you will put the correct letter if you randomly take, okay, if you choose one letter from n letters and you put it in one envelope, what is the chance that that envelope will have the correct letter? There is only one possibility out of total of. So, you can drag out 1 out of n envelopes in n different ways. Okay. So, your expectation of xi, okay, is nothing but, okay, 1 into probability of that is 1 by n, okay, x into the probability, it is 1 by n as we calculated, plus for all other cases it is 0, okay, because the xi is 0 and you know, so your x value is 0 and your probability can be anything. Okay. So, for all of them is also 1 by n. Okay. So, this is nothing but 1 by n. Okay. So, this is that the expectation that the first envelope is in the first letter is in first envelope. Okay. So, my total expectation then is similarly the summation of exi n times, right, 1 by n plus 1 by n times. What is the value then? 1 by n into n is simply equal to 1. Okay. So, it means that on an average, okay, only one letter will be in its correct envelope. Okay. Let's take another paper. Okay. So, we can generalize. So, you have x and you can have expectation of x. You have x plus y, your expectation of z. So, let us say if you define z is x plus y, E of z is simply E of x plus E of y. Okay. You can define a problem as a variable z as g of x. In that case, E of z is simply is equal to is E of g of x, right. And what is expectation of g of x? It turns out to be integration over minus infinity to infinity g x into whatever the probability distribution you had, okay, g x into f x into d x. Okay. So, let us take one simple example of how you can calculate expectation of a function. So, let us say in a plant, okay, in a power plant, okay. So, when there is a fault, okay, so fault or breakdown, it takes x amount of time, okay, x amount of time to fix the fault. Okay. So, and this x, so x is a random variable, continuous random variable. It follows the following probability distribution. Okay. Okay. This is the probability distribution. Now, you have, let us say, so there is a cost associated with one particular with this breakdown. The cost of breakdown is x cubed. Okay. So, the question is, what is the average cost of breakdown? Okay. What is the average cost of breakdown? What will you do? So, essentially you have a function g of x, which is x cubed, okay, and this is the corresponding probability distribution. So, essentially we are expected, we want to find out expectation of x cubed, which is nothing but 0 to 1 x cubed into 1 into dx. Why we had only the limit 0 to 1? Because this is the only place where your probability density with PDF has some value. So, this is nothing but 1/4. Okay. So, this is how you can define new functions, and if the underlying probability distribution is the same, you can find out the expectation of this new function, which is derived from other random variables. Okay. So, in expectation, so you have, let us say, a random variable x. Okay. We want to know, okay, we want to know what is the best descriptor, okay, best predictor that x, what is the prediction that x will have a value of c. Okay. What is the value of c which best predicts x? Okay. So, in essence, okay, we want to compute, okay, the best predictor of x. What should we do? We should minimize the difference between the value of x and the prediction. Okay. In other words, you want to minimize x minus c whole square. So, the best predictor is what will give you the lowest of expected value for x minus c whole square. Okay. So, I can write down this e of x minus c whole square, I can expand that. Okay, whole square. Okay. I can write it as expectation of c plus. Okay. So, I can expand them laterally. Okay. Plus expectation of, okay. I have the following expression. Now, what is the value of expectation of x minus mu? Okay. What is the value of expectation of x minus mu? Okay. Expectation of x minus mu is equal to expectation of x minus expectation of mu. Okay. What is expectation of x? It is mu. What is expectation of mu? Mu is a constant. So, expectation of mu is equal to mu. So, expectation of x minus 0, x minus mu is simply equal to 0. Okay. So, we can write this expression okay. We can modify this expression plus okay. So, your expectation of x minus c whole square is expectation of x minus mu whole square plus expectation of mu minus c whole square. So, since I can write this. So, expectation of mu minus c whole square is, so this is, I can further simplify plus okay. So, expectation, this is a constant. So, expectation of this constant is simply that value, okay. And mu minus c whole square is a square. So, this means that this is always positive, okay. So, I can write x minus expectation of x minus c whole square is always greater or equal to x minus mu whole square, expectation of x minus. So, this means that my mu is the best description okay. This is why the average is taken such a standard metric for defining the population or the sample, okay. So, while we have defined this, we can also define variance, okay. Variance, okay. This is defined as expectation of okay. So, variance is nothing but expectation of x minus mu whole square, okay. So, I can expand this okay. Okay. So, x expectation of x is simply equal to mu and expectation of mu square is simply equal to mu square, okay. So, this gives me, so you have minus 2 mu square term and a plus mu square term. So, this will give you a minus mu square term. So, variance of x okay. So, this is the final expression for variance of x, expectation of x square minus expectation of x whole square, okay. So, let us say for the die roll you have x values of okay 1, 2, 3, 4, 5 and 6, okay 1, 2, 3, 4, 5 and 6, and you have probability all of 1 by 6, okay. So, what is my variance? Okay. So, for calculating my expectation of x, so we have x p x and x square p of x, okay. So, x p x is 1.1 by 6 dot 6.5 by 6, and we had calculated. So, expectation of x we had already calculated before, it turned out to be 7 by 2, okay. Let us calculate the value of x square p x, it is 1 square dot 1 by 6 like this, 6 square dot 1 by 6. So, your E of x square is summation x square p x, okay, plus 4 square plus 5 square plus 6 square, okay, is 1 by 6, 1 plus 4 plus 9 plus 16 plus 25 plus 36, 1 by 6, okay, 14, 30, 30, 66 and 25, 91, okay. So, your variance of x will turn out to be okay 91 by 6 minus E x is 7 by 2 minus 49 by 4, okay. So, you can simplify this and calculate the final value of variance, okay. So, we have the following simplifications, right. So, E of a x is equal to a E of x, okay. What about variance of a x? Okay. Variance of a x is nothing but you will turn out. So, let us see, it is expectation of, okay, okay, it is expectation of a into x minus mu whole square, okay, a square. Okay. So, variance of a x, okay, is equal to expectation of x mu minus. Okay. So, you can take out the a square term, okay. Variance of a x is going to be a square variance of x. Okay. Okay. Variance of a constant is equal to going to be 0. Okay. So, you can also write down the expansion for variance of x plus y. So, this is a little bit tricky, but you will see that in the most general case it will come out to be variance of x plus variance of y, okay, plus, okay, 2 times covariance of x comma y, where covariance of x comma y. So, we have cov of x comma y is defined as the covariance, okay, is expectation of x minus mu x into y minus mu y. Okay. We will stop here for today, and in the next class we will briefly discuss about covariance, and then we will start discussing about 3 important random variables which are relevant to statistics. Okay. With that, I thank you for your attention and look forward to next class.